Okay, thank you. Hello, everyone. My name is Carlos Ferreira. I am from Brazil. I will present a work entitled of Understanding Mobility Networks, a node embed approach. Uh, and to understand the entity's mobility patterns in mobile networks is a fundamental step to design, to manage, and evaluate the performance of several applications and services in such contexts. Typically, this is done first by building a network model, as exemplified here, where nodes represent the entities and the links represent the possible data exchanges or potential data exchange among these entities. And as a natural consequence, many solutions, for instance, routing protocols and so on, were proposed based on topological measures computed on this network model as exemplified here. And the problem is that each measure provides a distinct notion of importance for a given node in such context. For instance, taking this network as an example, we have here four different network centrality measures. And as you can see, each one selects the best node according to uh, its particular criteria. For instance, the highest eigenvector centrality, the highest between centrality, it's more related to the flow of information in the network, the highest degree centrality, in this case, the node J is the most connected one, and the higher closing centrality and so on. These measures are not able to generalize the notion, the idea of nodes importance in the network. In light of this, our proposed here is a node embedding based methodology to model and analyze the mobility patterns over spatial and temporal dimension. More specifically, we are interested into capturing the node mobility and importance for connectivity in the network, and by making use of network topology and its temporal evolution. Our methodology starts from a data set where we have users or entities interactions, as you can see here, and we have also a period of interest. Then we propose to discretize this period in some no overlap and fixed time windows, as you can see here, from delta T1 to delta Tn. And the next step consists in to model the network, a network model for each time window. And then we propose to represent the sequence of network models into a low dimension representation. As you can see here, where we preserve the nodes proximity in the network in the low dimension representation, and also we capture new connections, we capture the node shifting in terms of connection, in terms of mobility in this network, in this low dimension representation here. To do it, we employed a method called of dynamic node to back. It was proposed in the literature, and it is based on node to back, one of the most famous methods for node embedding. The idea is that for each time windows and for each graph model, G delta T, it performs a sampling using a bias handwalker. This bias handwalker to those node to back is the same. Then the idea is to set a number of walkers for each node and define also the number of steps that each walk will do, as you can see here. And this sampling process is based on a breadth first search. In this way, we can sampling the neighbors, the more closer nodes in the network. The next step then is to build these concurrence metrics by the sampled paths in this in the network, where the intuition of this metrics it is also known as pointwise multi-information metrics, but the intuition here is that the greater the coherence between two nodes in the simpler paths, the closer they are in the network, and the more important is the connection between them. Suppose that we have a node in this point and it has just one edge. So these two nodes will appear a lot in this matrix. Then it makes it very informative. Once that we have a sequence of these metrics for the sequence of the network models, the dynamic node2vec will use then to produce a sequence of time-aligned embeddings. But what is time-aligned embeddings? Just to clarify, here we have another toy example. It's just a simple network, and then we do the sampling process using the bias handle algorithm for a given time window, in this case delta T1, and then a dynamic node2vec apply a function to encoder this representation to obtain the representation in low dimension representation. It's not a two-dimension, but it's just for the sake of visualization. We can apply PCA, Disney, and so on. And here we have the two corresponding groups, as you can see here, the two disjoint parts of this network. And focus on this specific node, this black node, we can observe it's here. And for another time window, we have the same network, but just this node, this specific node has changed its connection. Then the assembly process is the same, the encoder is the same, but the representation is time aligned. I mean, the other nodes that have no change, it's in the same position or almost in the same position, while this node that totally changed its connection, as you can see here, it's now in another position in the vectorial space and latent space represented. So it allows us to track to what extent nodes change their connection over time. It's work more or less as I explained here. And then for this representation time aligned, we can extract some patterns. At least two metrics can be used to do it. The first is a cosine distance, where we can quantify the node connection change between two distinct time windows. And in this case, values close to 0 indicate that a node keeps its connection, and one is the opposite. And the second one is the vector norm. I will not enter in details, but by design, in dynamic node2vec, the more a node appears in the simpler paths in a given time window, the greater is the norm of its vector. So we have the indicative of the node's importance to the network connected. Once that a given node appears a lot in the simpler path, it's quite important for the flow of the information, for the connectivity of several other nodes. Okay, moving to our case study, we use a model from the literature. It is called a group regularity mobility model. It is based on the dynamics and the regularity of social meetings. It assumes that some groups of people regular meet in some place, but also in a sporadic way. The advantage of this model is that it's take as input a real trace, extract some important characteristics, for instance, the time between the social meetings, the size of the group of people meeting, and so on, and can generate some synthetic trace with the same properties. And here we use just as a proof of concept a dataset provided by the authors, where we have 100 users covering a period of 87 days, and we analyze the mobility of these users, this group of users, using daily time windows. Then, starting our results, we first analyze it to what extent do nodes change their connection. As I explained, we use the cosine distance, and then we compute the average of cosine distance per node to build this CTF, where we can see that some averages are small and others are in some sense high, indicating that nodes have different levels of mobility in this network. And we also analyze the variation around this average. And to do it, we use the coefficient of variation of this cosine distance, where we can see that some nodes present a high coefficient of variation, indicating that these changes tend to be irregular. I mean, although the average may be small, but and sometimes they do abrupt connective change. To exemplify in terms of the average of this time or average of cosine distance, we took as an example the node with the highest average cosine distance in all period analyzed. And here we have a heat map where we have the period analyzed, and we have for each cell the cosine distance for 2 given days. As you can see, most part of this grid map is red, indicating a high indeed array mobility array cosine distance that captures the idea of the nodes are changing, that the node is changing its connection. And conversely, we also took the node with the lowest average cosine distance, as you can see here, and the most part of the grid map is blue, is clear, and indicating that this node is in some sense stable in terms of connectivity. We also analyzed the distribution of the importance of the connections established by the nodes. And once again, we computed a CDF. In this case, is the average of vector norm per node. Again, we can observe some variation among the nodes in the period analyzed, but in terms of coefficient of variation on this average, we can observe a higher coefficient variation distribution, suggesting that nodes have temporal importance in terms of connectivity into the network. Sometimes they are quite important, sometimes they are not so important. And then to investigate better this aspect, we built this grid map where we have the period observed and we have the nodes in the y-axis. In this case, it's people, users. And we have for each cell the vector norm of a node representation for a given day for this specific node. It should be noted that is normalized by z-score, so we are looking at the relative deviation. We also computed the dendrogram, looking for nodes with similar importance idea in the same day. And as you can see here, we have small groups of nodes of users in specific days with momentary connectivity importance. In some cases, we have also some groups of users that are not important for connectivity in these some specific days. So it's quite dynamic. Last, we analyzed the relation between the embedding measures that we are proposing here with the topological ones. We selected the most used in the literature. Part of them are indeed quite used. For instance, the average degree between is close and so on. And starting by the cosine distance that captures the dynamics of the node, we can observe that we can observe a moderated negative correlation, suggesting that the more dynamic a node is, the lower its centrality. And in terms of connective importance, again, we are talking about the vector norm and the centrality of the node in the network. We can observe a low to moderate positive correlation, indicating that nodes' connective importance may not be explained by centrality metrics, as you discussed in the beginning of this presentation. In conclusion, This is our work. This is still a work in progress, but we have observed that our approach offers an alternative notion of connective importance. It allows tracking certain aspect while the connection, the network evolve over time. This is another important idea because the network is in some sense dynamic. And suggest that topological network measures, at least for this case studies as a proof of concept, could not generalize the patterns of connectivity captured here. As future work, we intend to incorporate this idea in solutions for dissemination and collection of information in mobile networks, and also evaluate the performance of protocols comparing purely topological measures to those proposed here. That is all. Thank you, everybody. And all questions are welcome.
Thank you, Carlos. So, questions for Carlos? So, Carlos, well, we know each other and I know your work, and so I have many questions, but I will keep them, most of them, for later offline. I just wanted to ask you one question here. So, you have to choose a delta time for the dynamics, right? And my question is, how can you choose this delta time? So it's like given from the domain knowledge, if it's 1 second, 1 day, or do you have an automatic way to find out what is the delta time appropriate? Because sometimes, you work on something, on data, and you're not really sure on which level you want to see the dynamic.
Okay, I got your point. We chose the time window size based on the dataset characteristic. In terms, I'm not sure the number, exactly number now, but I believe it's around 90% of the meetings occur in a daily time windows. Then we aggregated the contacts, the meetings of people based on this information. I believe it's around 90%, 95%, something like that.
Okay, thank you. I will send you. I think I will write you other questions because I'm really curious about this work. Are there other questions from the audience? If not, we can close here. And I don't know if. Thank you again, Carlos, and thank you to all the presenters.